figure out which number it is, involves two binomials, and there's two different sample sizes. I know that can be a bit confusing, so think about the likelihood function as just the product of those two different binomials, and they're independent, right? The x1 is one binomial, the x2 is independent. So the way to think about the central limit theorem in that case is just put just use two separate n's. So root n1, the first sample is from a binomial of size n1, and the second sample is from a binomial of n2. You can assume they're both going to infinity. So let's just write it this way: root n1 times p hat 1 minus p1, and root n2 p hat 2 minus p2 is going to normal, mean 0 with some covariance. And they're independent, so in fact, so the diagonals of this will be 0. Just think of it as two central limit theorems. The other one that's I think this is word-worthy, question 7-8. I say, what does something converge to when the model is wrong? I should have said more specifically a specific wrong model. So you can take the wrong model. The rest of the question assumes the data for normal. So for this part, you can assume that it comes from a mixture, which means every observation is drawn with probably 1 minus epsilon from the normal. But say with some probability epsilon is drawn from an arbitrary distribution Q, where Q just has some other mean here. And you can do all your calculations under that specific wrong model. So when I say assume the model is wrong, you can assume specifically that this is the model now. And we're asking about what happens when we're trying to estimate a function of data, pretending we've computed the estimator assuming that the model is actually normal. Now we're asking what would happen to the estimator, what would it converge to in this situation. So that should make those two questions more concrete, I think. Yes?
For the binomial question, the covariance matrix for two Bernoullis instead of binomial?
This is binomial. Well, no, you're right. Sorry, you're right, because I put the root n on the other side. That's right, it'd be for two independent Bernoullis. You don't have to assume this, but this is a way to make that. The statement is a bit vague in the question. So this is a way you can make it concrete. If you have a different way of doing it, that's fine. Any other questions about the homework or about anything else? Everybody's happy? All right. So we want to start talking about hypothesis testing. Remember that what I said last time, keep in mind that hypothesis testing really is, I'm teaching it to you as a tool that's going to help us do other things. Actually doing hypothesis testing is something that in data analysis is something we do sometimes, but perhaps not too often. And the problem is this: so far we've been trying to estimate a parameter, and we're still going to stay in the parametric framework. We're going to finish doing hypothesis testing and confidence intervals in the parametric framework. Then we're going to drop parametric inference and switch over to non-parametric. But for now, we're still in parametric land. And instead of trying to estimate data, we're trying to test. You might think of it as testing a theory that theta takes a particular value or is in a particular set. So the typical way this is expressed is we have what's called a null hypothesis, which might take the form theta is equal to theta 0, and some sort of alternative hypothesis. So this is the null, and this might take the form theta is not equal to theta 0, and we're trying to ask the question. If we're starting with the null assumed to be true. That's the beginning point of the hypothesis. And we're trying to say, do we have enough evidence to reject this null or not? And it doesn't have to be, this is the most common form, but it could be, the null could be theta is less than theta 0, and the alternative could be theta is bigger than theta 0, or there's all kinds of variations. We call a hypothesis like this simple. This is called composite, because there's more than one. We can have, more generally, we just have the null hypothesis that theta is in a set. and the alternative could be that it's in a different set. The only thing we would require is that these are different, so that theta 0, theta 1 is empty. And this will, as we go through examples, these types of hypotheses will become clear. But it's going to depend on the context. And so let's start with a really simple example. Maybe you're working for government and there's some accusation that this casino is cheating. So you want to, the null hypothesis might be that the dice they're throwing are fair dice, everything has an equal chance of coming up. The alternative is that it's not. Or maybe a lottery would be another good example of that. Or the simplest one would be a coin. You have this null hypothesis. We're using this coin thinking that it's fair, so that you might start off by saying that the null hypothesis is that t is a half. And that the alternative is that it's not a half. And you're going to flip the coin 100 times and try to make a decision here. Okay, and so the thing is, though, that hypothesis testing is a very asymmetric situation. It's set up a very specific way, and it's very much like a legal case. When you get accused of a crime, hopefully you won't be accused of a crime. You get accused of a crime, you go to trial. You start with the presumption of innocence. And the question is not whether you're innocent or guilty. The question is whether there's evidence, sufficient evidence to reject your innocence. Okay, it's about evidence. And without that evidence, we retain the null hypothesis that you're innocent. And that's how hypothesis testing is done. So in hypothesis testing, it looks like this. There's let's say the world. The true world is that either this null hypothesis that we're starting with, this is our beginning hypothesis, it's either true or it's false. In other words, either H0 is true or H1 is true. Actually, let's always write this as H0 is false. And then there's the actions you can take or the decisions you can make. And in this particular framework, we're only allowing ourselves two possible things, which is to retain the null hypothesis. Remember, we're starting out assuming the null is true. And the other thing is to reject. So to have another example of this in mind, we could be testing a drug versus a placebo. This is what will happen if you're a drug company and you want to convince the FDA to approve the drug. You might start off saying it's no better than a placebo. That's the assumption. And now you've got to convince them that you have evidence to reject that you're better than the placebo. Okay, so this is this situation here. Either the null is true or false, but your decision is either going to be retain the null or reject the null. And so if the null is true and you don't reject it, great, you have not made a mistake. If the null is false and you rejected it, that's good too. But the other two situations are errors, and we need to give them names. Statisticians are not so good at coming up with cool names. It's one thing that computer scientists are much better at. So statisticians call this a type 1 error. How's that for a boring name? You can think of it as a false positive. Maybe that's a better name. False positive. Because what's happened is you said, yes, the drug works, but you were wrong. It was just a chance finding. The other one is that maybe you should have rejected it and you didn't, so not surprisingly, that's called a type 2 error. Another exciting name, or a false negative. And generally, hypothesis testing is used in a framework where false positives are worse. You don't want to make a false positive. That's the biggest error. Like, all of a sudden you say, oh, everybody should be eating broccoli, it's good for you, and then millions of people broccoli, it turns out you were wrong, and now you're like killing everybody. So you don't, it's a very asymmetric situation. Otherwise, you shouldn't be doing this hypothesis testing. Type 2 error is more about your career. You could have made a big discovery and gotten the Nobel Prize and you missed it. So you've hurt yourself, but you haven't hurt society. That's kind of the way. So the way hypothesis testing, so again, hypothesis testing should only be used if this is appropriate for what you're trying to do. Usually, I think, again, these are rare situations. They come up, but a lot of times I see people using hypothesis testing where I don't think it's hypothesis testing problem, it's more of an estimation problem. So we're going to proceed here assuming we're, for whatever reason, we're in a hypothesis testing framework. And the game is going to be this. What we're going to try to do is design good tests. And what's a good test? First and foremost, we're going to follow, who was it? Hippocrates, first do no harm. Make sure we control the false positive rate. We're going to set some rate, like 5% or 1%. So we want to set things up so there's only, so if when the null is true, I want to make sure I only make mistakes of at most 1% of the time, or whatever rate we want to set. The rate that we set is very dependent on the field. So in medicine, it's often set at 5% or 1%. In particle physics, it's something like 0.00001% because they spend billions of dollars building some sort of particle collider. They say they found a particle, somebody wins a Nobel Prize, and so on. The whole field changes. They want to be really sure that they haven't made a false positive. So they tend to have a much stricter rule here. Now, there's going to be lots of tests. We're going to construct these hypotheses. There's going to be a lot of them that control the false positive rate at the desired level. So we want to try to choose one which minimizes, in some sense, the false negative rate, but only once we first control the false positive rate. Again, you see this asymmetry here. First control the false positive rate, try to find among those ones, try to find the best one. So that's going to be the goal of hypothesis. And so we're going to do it just like we did estimation. We're going to first construct tests and then study their properties. I do need a little bit of notation that's going to come up repeatedly throughout here, which is if this is a standard normal distribution, so this is just a normal 0, 1. This guy here that has probability alpha to the right, we refer to it all the time, so we usually call it z sub alpha. So in other words, the probability that a standard normal is bigger than z sub alpha is alpha, or to put it another way, z sub alpha is the inverse CDF at 1 minus alpha because the amount of probability to the left will be 1. So that's just a number. So for example, when alpha is 0.05, z sub alpha is about 2. And of course, if I put minus z sub alpha here, that would have the probability alpha also come out. So that's just a little bit of notation that will come up. So how do we construct these tests? Well, we basically make up a rule that says we're going to reject the null hypothesis whenever something happens. So we're going to, that really involves creating two things. Some sort of statistic. This will be our test statistic. This is going to be the thing we're going to compute, do the test. And then a rule for when do we decide to reject it. Well, that's going to involve a rejection region, R. This is the rejection region. So we reject the null hypothesis if T is in the rejection region. So it's clearly we have to do two things here. Reject null. We have to construct an appropriate test statistic, and we have to construct an appropriate rejection region. So like in the coin flipping example, I think you can intuitively figure out what to do. Flip a coin 100 times, and if the proportion of heads is really far from a half, we would reject the null hypothesis. That would be an example of a well-defined test. So there are, lots and lots and lots of different tests. we're going to talk about 4 specific tests that I think cover 99% of the situations you're going to deal with. There's the Neyman-Pearson test. The Neyman-Pearson test is not something that you use in practice a lot because it's very limited. But it's an important test for theoretical reasons, so we start with that. Then we'll talk about the Wald test, which is sort of, think about that as the analogy to doing maximum likelihood estimation, the testing analog. Then there's a more general test called the likelihood ratio test. And finally, there's something called the permutation test, which is a very, very cool test. It's also a little bit limited, but when it's applicable, it's a really, really good test to use. So we're going to talk about all of those, but for the moment, let's say somehow somebody's come up with a test statistic. Let's put that aside for the moment and think, how are we going to decide what the properties are of this thing? And ultimately, we can think of the rejection region as really as just some subset of the sample space. So there's going to be some set of samples where we're going to reject. And so we define this function, beta of theta. Let's just say we have a single parameter for the moment. So I'll just write it like this. And what I mean by this is just the probability we reject H1. What we can do is say for any particular value of the parameter, suppose we fix the value of the parameter or set of parameters at some value, say what's the probability of rejecting the null? And now that's going to be a function of the parameter theta. And here's what's going to happen. We want this to be small when the null hypothesis is true, and we want it to be large when the null hypothesis is false. So here's the general strategy we're going to follow. We fix alpha. This is the amount of type 1 error we're willing to tolerate. And again, this could be very, very problem specific. No test is going to be perfect. So we're going to have to decide, if the null is true, there's going to be some chance we're going to make a false claim. How high are we willing to tolerate that? And so the way we're going to proceed is we're going to try, we need to make sure, I would like to maximize the probability of rejecting this for different values of theta, except under the null. So this is for theta under, let's say, the alternative. I want to make this as big as possible, but subject to for every theta in the null. Now sometimes the null is just a single value, but sometimes it's a set of values. Okay, so let me draw a picture. What's going to end up happening, let's consider a simple case where there's one parameter and where the null is just a single value, so theta is 0. And imagine I compute the probability of whatever test you have. I'm going to say, what's the probability to reject this null hypothesis? So here's alpha. By definition, I need to make sure that the probability of rejecting when the null is true is never more than alpha. But it might be higher at other values. Hopefully it's higher at other values. So in some sense, what we're trying to do, this is called the power function. We're trying to solve a kind of optimization problem here. We're trying to make this power function as big as possible, but subject to the constraint that at the null, it can't be bigger than alpha. Okay, and if you give me 2 different test statistics, they could have been power functions. So we're trying to find a good one. Makes sense. This alpha is called the size or the level of the test. It's called size alpha test, means we're controlling the error rate of alpha. Okay, any questions so far? This is the setup. All clear?
Can you explain this a bit more? Like, why are we trying to do this kind of shape?
Well, if the null hypothesis is true, I want to make sure the probability of rejecting is alpha. Okay. But if the null is false, I want to have a high probability of rejecting the null hypothesis.
And why couldn't we have like a lower probability of rejecting in the null?
Oh, yeah, we could have it less than or equal to this, that's true. That would still be a valid test.
Okay, so
Yeah.
that
Yeah, it should be somewhere in here.
Okay.
So imagine that the set is continuous, like incoming many values. So now talking about a specific value of theta and talking about the probability of that doesn't seem that meaningful, like it is zero. And so I don't understand, like, are we talking about densities, but why that makes sense?
Well, don't forget, the data is not a random variable, it's a parameter. And so what you're asking is, why would we care about theta having a very specific value? And that's why I say hypothesis testing is rather special. So if it was a treatment effect, you know, we might want to say, I could be giving you vitamin C and probably that has no effect on the disease. And so the null hypothesis, so as the FDA, I'm going to assume the effect is zero until you can convince me otherwise. So zero has a very special meaning in scientific. But in lots of cases, it would not make sense to say, why would I care that testing theta is equal to 0 or 3.7, then we shouldn't be doing hypothesis testing. So that's why I keep saying hypothesis testing is a very special thing that we're not normally going to do, although we'll see mathematically it's going to be very useful for constructing confidence intervals. So from our point of view, most of the time this is just going to be a step towards creating confidence intervals. But to actually do hypothesis testing, you better have a scientific plausible reason for why you're testing that very specific value. And you're absolutely right, that in a lot of cases you see people doing hypothesis testing and you go, I really believe that theta is equal to 0 exactly, it just doesn't make sense. That's why there's so much criticism, or one of the reasons why you see criticism in the press about hypothesis testing. But so we're tentatively, proceeding here, assuming that this framework makes sense. Let's actually work out the power function in a very specific example. We're going to start with examples, then we'll turn to kind of more general methods for constructing tests. But for the moment, let's just start with the simple one. The natural one to start with would be our easiest distribution, which would be normal. And in fact, let's take sigma squared to be a known constant. So we're going to make it a one-parameter problem. The only thing that's not known here is theta. And actually, I'm going to change it a bit from the notes. I'm going to say, suppose the null hypothesis. In the notes I have theta is equal to theta 0. Let's make it a little more interesting. Let's suppose the null is that theta is less than or equal to theta 0. And the alternative is that theta is 0. So maybe again, this is some sort of treatment compared to placebo. And I'm going to say, bad numbers are small. I'm the FDA. My null hypothesis is that this is no better than placebo, or maybe even worse than placebo. That's my null hypothesis. And I'm not going to prove it to you to convince me it's better, which would be theta is good. So that might be a reason why we would construct the null and alternative this way. So this is what's called a one-tailed alternative, because it's only in one direction. And they're both composite, you can see, because it's not a single value, it's just a set of values. Well, I'm just going to make up a test statistic that will probably seem at least intuitively reasonable. I'm going to compute the mean and compare it to theta 0. So I'm going to call the test statistic Tn. I'm going to take x bar minus theta 0. But actually, we're kind of used to standardizing these things now. It might make sense to standardize this. I'm going to standardize it. In other words, I'm dividing this. It's how far this is in some sense from the null divided by its standard deviation. So I'm going to do it like this. That might intuitively seem like a reasonable test statistic. And when would you reject this null hypothesis? Well, if t is big, it seems like a reasonable thing, right? If this statistic is big, that means x bar is far to the right of the null. That seems like, without any theory, just common sense, that seems like perhaps a reasonable rejection rule. So what I'm going to do is I'm going to reject the null hypothesis if Tn is bigger than some constant c. How am I going to determine c? Well, I'm going to determine it because I want to double alpha fact, what's going to happen in this case, because of the one-sided nature of the null and the one-sided nature of the alternative, we're going to see that when I draw the power function, it's going to look a little bit different. It's actually going to go like this. It's going to go to 0 this way. But I think you can kind of see that, right? What's the probability that Tn is big? As the mean gets bigger, that probability should increase. So it's going to look something like this. A bit different than the power function I just drew. And to make sure that it's the level of the test is alpha, I use level and size, by the way, interchangeably. Technically, they're a little bit different. The notes clarify them. But it's a small distinction. So I just keep using size, level. I just mean the type 1 error is going to be no more than alpha. Well, where's the null? The null is all this stuff. And this is the alternative. I want to make sure under the whole null, I never reject more than probably any higher than alpha. You can see the worst case is going to be here, right? So what I have to make sure is that under the null, this curve stays under alpha. Let's actually do the formal calculation. So, yeah.
Why not choosing just an indicator, for instance? Like, if the theta is bigger than 1, if the
No,
theta
we
is,
don't know theta, we only know x bar.
that is an estimator of theta.
Right?
So we should
So-
just do an indicator.
Oh, why not just reject our x bar is bigger than a constant?
Yeah.
That's the same, right? I could rearrange this to write this as
Oh, so
x bar bigger than some other constant. So that is exactly what we're doing. But I wrote it this way because this is easy to do calculations with. But yeah, I could say this being bigger than c is the same as x bar bigger than some other constant. So let's actually compute the power. What's the probability of rejecting when the true value is some arbitrary number theta, not necessarily equal to the null? Well, that's the probability in fact, I'm going to do just what you said. I'm going to rewrite this now. See that this looks like calculations we've done before, except for one small point. This statistic, this statistic I constructed has the null in it. I'm comparing how far x bar is compared to the null. But I'm not assuming the true value stays. So I've kind of standardized this wrong. From the point of view of doing this calculation, I kind of like to have theta there. So what I'm going to do is rewrite it just like you said. I'm going to rewrite it in terms of x bar. So this is the same as saying that the probability that x bar is bigger than sigma times c over root n. That's another way. You could just call this whole thing c prime. That's really all we're doing is we're rejecting when x bar is bigger than some constant c prime. Now I'm going to re-standardize it in terms of the true value. So now I'm going to say, I'm going to take x bar n, and we're doing this under the assumption that the true value is theta, so I'm going to subtract theta. Okay, so that's bigger than sigma c over root n. But now again, we're used to converting this into something that's a bit easier to work with. Like we're going to multiply that by root n. So that gets rid of that. So this makes this. And now I'm going to divide through by sigma. So that gets rid of that. And the reason why I'm doing that is because when theta is the true value, that makes this equal to what's the distribution of that? Standard normal, right? And this is equal to the probability that a standard normal is bigger than c plus root n. Everything here now are constants. This is, we're using z to be. So I just re-expressed it all that way so we have it as a simple quantity. Of course, the probability, we're going to always use capital phi for the CDF of the standard normal. So our notation will always do this. Actually, this is 1 minus that. So this is just 1 minus d of c plus. Now, if you plot this as a function of theta, Remember, sigma's fixed, C is fixed at the moment, we just arbitrarily fix C, root n is fixed, theta 0 is fixed. The other thing that's changing is theta, and you'll see you get a function that looks like this. But there's a C I have to determine. But I know something. I know that when theta is equal to theta 0, I want this to be alpha. So let's set, if I set theta, so if I want theta of theta 0 to be alpha, well, look what happens. When theta is equal to theta 0, this is 0, this part disappears. So what I get is that 1 minus phi of C has to be equal to alpha. Or in other words, phi of C has to equal 1 minus alpha. C has to equal phi inverse 1 minus alpha, which is what we call Z alpha. So in order to have a size alpha test, in order to make sure that under the null, the probability of error is always less than alpha, usually taken to be 5%. I know what, that determines this cutoff. We now know that the test is reject the null if root n x bar minus theta naught over sigma is bigger than Z alpha. Everybody with me? Of course, the form of the test to start with, like deciding to use x bar, may have seemed somewhat arbitrary, but maybe not, because we know this is, for example, the maximum likelihood estimate. Yeah.
Can you say how do you get from the first one to the second one?
Here to here?
Yeah.
Oh, I just subtracted theta from both sides, multiplied by root n on both sides, and divided by sigma.
But then why the theta is a function of theta, and there is no theta in the first one? There's only theta 0.
Well, this should be a theta here. This whole thing is dependent, yeah, on the true value of theta.
We're assuming that b of theta is equal to alpha in that boundary because in that sense we're maximizing after.
Well, you can check that this is an increasing function. And so keeping the type 1 error less than alpha over the whole null corresponds to making sure that it's no more than alpha exactly at the end of it. Like we keep it less than alpha here, then I keep it, and I just have it equal.
And if you say beta of b of theta 0 is going to be less than, strictly less than alpha in that point.
That would hurt me, because I want to also make it as big as possible as I can over here.
No, I didn't.
In fact, as it turns out, this is a uniformly most powerful test, we'll talk about that later, that it has the highest possible power subject to controlling the type. And another thing you can see is it's actually a good exercise to plot this power function, because as n gets bigger, here's what happens. This starts to look like this. Power function will always keep the type 1 error at alpha by construction, but the slope of this function increases with n, which makes sense. As you have more and more data, your ability to discover that the null is false, your ability to reject the null, gets higher and higher. You have more information. So it's easy to check, it's a good exercise. If I take any alternative value, say here, this power function converges to 1 as n goes to infinity. Which is pretty intuitive. Now, what happens if I change this to be these one-sided tests, like I just did? They don't actually come up so often. More commonly in practice are tests like this, a simple null and a two-sided alternative. So if we did exactly the same thing, what would we change here? Well, probably we'd want to reject if t was either really big or really negative, big in either direction. So the natural rejection rule would be reject if the absolute value of t is bigger than c. And now you can do exactly the same calculation, and it's done for you. Probably page 4, you should go through it. Where I just have to compute the probability of rejecting. There's two ways to reject. The probability that x bar is really big, or the probability that x bar is really small. And if you do that, I've done the calculation for you. You do get a power function that has a different shape, because you're going to reject if it's really big or really small. So it looks like this, like the first one I drew. And if you set this equal to alpha, you don't get, because there's two ways to reject. There's a probability of rejecting on the right, probability of rejecting on the left. You have to sum them together. That's what this is, it's summing two of them together, and they have to add up to alpha. So the rule ends up being here, reject if z is bigger, if t is bigger than z, alpha over 2. The 2 comes again because under the null hypothesis, the probability of a false rejection, we're going to reject if we're big or if we're small, and we have to sum two things together. So you have to make sure each one is alpha over 2 and that it's not alpha. So you should go through that calculation at the top of your page, make sure you see where that's coming from. But that's the difference between a two-sided alternative and one-sided alternative. Is in a two-sided alternative, you're going to reject, if it's really big or really small. In other words, if the absolute value is big, and the critical value, this is called the critical value for the test. It changes. Instead of being z alpha, it's z alpha over 2.
The case that mapping on the left would go to a normal, would go to a normal random variable in the limit.
Actually, it's exactly normal. Right? We're assuming the data are normal. This was a normal example. So this is exactly standard normal. Now, more generally, you're right. The asymptotic test will be. Any other questions? These two tests are the canonical tests. So it's important to understand the calculations that I just did. Go through the calculations of those, because every test we're going to do in the future is really some version of something like this. Okay. So, good. So I think this is sort of the basic framework of testing, but we really need a more general way to come up with a test with this thing. X bar seems reasonable there. In a more complicated situation, it might not be so obvious how to construct a test statistic. Remember, we have to come up with a test statistic, and we have to come up with a critical value, a rule for when to reject it. So that's why we're going to go through these 4 tests, because these are the most common tests. So let's start with the first one. This is called the Neyman-Pearson test. Neyman was a statistician at Berkeley who created a lot of statistics studying. Pearson was an Englishman. He was an English statistician. This is a very specific test. It doesn't get used much in practice, but again, it's important to understand it conceptually. Because the reason why it doesn't get used is we're going to consider a very, very specific null hypothesis that say theta is equal to some null, theta 0, but also that the alternative is simple. So this is like saying under the null, the data come from a distribution with this specific parameter. The alternative is that the data come from this specific parameter. So like under the null, the data are normal 0, 1, and under the alternative, they're normal 5, 1. This doesn't happen very often. More in practice, hypotheses tend to be you're testing a specific null, but the alternative will just be some unspecified thing. This test is just testing a specific parameter for the null and a specific parameter, a specific distribution for the alternative. So again, this is kind of a rare situation. You don't see these kind of tests coming up that often. But for theoretical reasons, it's important to understand this is kind of the simplest hypothesis testing situation you could imagine, and so it's worth understanding how to do the test here. So what we want to do is I want to do the following thing. Let's think about what the power function is going to look like. So well, there's only two values for the parameter. So I don't get a curve. There's only the power here and the power here. And I want a level alpha test, so I'd like the height of the power function here to be alpha. And now we have a very, very, very specific optimization problem. How can I make the probability of rejecting the null, how can I make the probability of rejecting it as large as possible here while making sure it's alpha here? And the Neyman-Pearson lemma, as it's called, gives us an exact answer to this. What we do is the test statistic is simply the likelihood under the alternative over the likelihood under the null. So in other words, this is we're going to assume here that these are well-behaved probability density functions or probability functions. Let's say probability density functions. So I can write this down, and I just take the ratio. I'm just comparing the likelihood at the alternative to the likelihood at the null. And intuitively, it seems like if the likelihood's bigger at the alternative, maybe I should reject it. So I'm going to reject the null. If Q is bigger than C. How do I pick C? Well, if I take the null hypothesis to be true, this is just a random variable. Forget that it's densities, I've just given you a random variable. Under the null hypothesis, I could say, what's the distribution of this thing? I could even simulate the distribution if I had to. I could just simulate data for the null and compute this thing, and I could find a constant C that makes us have level alpha. In other words, we choose C so that the probability under the null bigger than C is exactly alpha. This is in principle something we can always compute. Because when I specify the null hypothesis, I've specified the complete distribution. I'm telling you the distribution. And I'm asking you, when that distribution is true, if I simulated data and computed this ratio, how often is it bigger than C? And we can either do that analytically or by simulation, whatever. And we adjust C. As C gets bigger and bigger and bigger, this is going to get smaller and smaller and smaller. So we choose C so this is exactly alpha. So this completely defines the test. And now the theorem says this is the most powerful test. Of all tests that have type 1 error alpha, that make this alpha, it makes this as big as possible. This is the most powerful test. I didn't include the proof in the book. Maybe I regret that, you know. It's not that difficult, but we're just going to take it as given. So the theorem says that if we have another test, suppose we have another size alpha test. It's going to have some power function. Let's say the power function call it beta prime. So you can make up some other tests. You can be inventive and come up with some tests. But the Neyman-Pearson lemma says that what's called the power function for the Neyman-Pearson test at beta 1 is going to be bigger than or equal to your. If you manage to find some other test with type 1 error alpha, I guarantee you the Neyman-Pearson test will have at least as much power, if not more. So that way, at least in this simple problem, there's no question about what test we should do. This is the most powerful test with size alpha. You just had that look on your face like you wanted to ask.
Just to know, I think the inequality is flipped in the notes, just so you know.
The inequality is flipped in the book?
In the notes, in the
No,
notes.
it's, oh, let's see. That's unfortunate. Yeah, so that's backwards. No one's ever noticed that before, isn't that amazing? It's the Neyman-Pearson test, thank you, that has the highest power. The way I wrote it in the notes is backwards. So. Like this.
So can you explain a little bit more what does it mean that we, like, so what if the true theta value is something that does not fit a 0 and not fit a 1? What, like, do we want to get? Do we want to say that theta, that h0 is true, or is it false?
Well,
But h1 is still false.
we're assuming here there's only two possible values, and we're definitely distinguishing one as the null. So we're starting off by saying, this is the null value. What we want to have are two properties. If the null is true, the probability of a false rejection cannot be more than alpha. That's the first restriction. So if theta 0 is the true value, I want to make sure whatever test you have, that the probability of rejection is no more than alpha. That's a constraint. Now, subject to that constraint, I'd like, if theta 1 is the true value, I would like to reject the null, and I want to make that probability as big as possible. So that's why it's a very restrictive scenario. You can think of it like you're testing whether some particle exists. And if the particle doesn't exist, we have some scattering parameter which is known to be 17. But somebody posits there's this thing called the Higgs boson, and we worked out that if it's true, then the scattering parameter should be 27. Now, I'm just kind of making this up. And so, have you discovered the Higgs? Well, we're going to start to make sure we don't want to make a false claim. So the first requirement is that if the null is true, if there's no particle there, you only have an alpha chance of making a mistake. But now, of all the, there's many tests you can construct with that property. You can find lots of tests that have only, say, a 5% chance of an error. I want to make sure, though, that if the truth is over here, I have the highest possible chance of rejecting it. And of all the test statistics you can construct, of all the tests you can construct, this one maximizes that, by the way.
So is it always true that h0 union h1 cover all possible?
No, this is definitely not true. So again, think of this as a real value parameter. We've now focused our attention on two particular values. That's it. So that's why, this is an important result, I think, conceptually, just to get some sense of what's going on. But that's why it's not so useful in practice, because we're not very often in that situation. In fact, what we're about to start talking about is, what do we do in practice? We're not going to use the Neyman-Pearson test very often in practice, although it does give us some suggestion, right? That maybe the likelihood ratio might play an important role. So what I'm going to do is tell you the three most common tests that are used in practice, which is the Wald test, the likelihood ratio test, and the permutation test. Now, what we're not going to do, though, so remember we did all that mini-max theory? We could construct testing from the same point of view. I could try to say, in every situation, can we say what is an optimal test and so on? That's a long path, and I think we've done enough of that for point estimation. We're going to take a much more pragmatic view. I'm just going to tell you the test statistics that actually get used in practice and what their properties are. They do satisfy certain optimality properties that we won't talk about. So we're not going to try to go into the theory of optimal tests. I'm just going to tell you test statistics and how we use them. And I'm going to right now tell you, in the scalar case, so what I mean by the scalar case is, in the case when I'm testing a hypothesis about a parameter that's real value, that's what I mean by scalar, as opposed to a vector. And I want to test this, and we're in the And we're in the parametric framework, where we're going to see on, well, by the way, Friday's a holiday, did you know? Okay, Friday's a holiday. Monday, so what we're going to do on Monday is I'm going to show you that the most commonly used test statistic, I would say, is what's called the Wald test, after Abraham Wald, he was a statistician in the 40s. And it's you take the MLE minus beta 0 divided by the estimated standard error, which would be, let's say, from the Fisher information. So it looks just like the test we just did for the normal, and we know this is asymptotically normal, right? So we're going to be using asymptotic normality, and what we're going to do, this will be the test statistic, and what we're going to end up doing on Monday is we're going to say, okay, we'll reject the null hypothesis if this is bigger than that normal cutoff. And this will not be an exact test, but the probability under the null of rejecting will not be exactly alpha, but it will be asymptotically alpha. And then goes down. Let me say that in testing and in hypothesis testing and in confidence intervals that we'll discuss later, we're going to make a lot of use of this asymptotic stuff, but it's only for computational reasons. I'll explain later in the course that in principle we can always do things exactly without any approximations. It's just that it's very computationally expensive to do it. So often we're going to use these asymptotic approximations so that this test doesn't actually control the type 1 error exactly at alpha. It's only approximately at alpha, because then it's large. But it's very simple, right? You can see how easy this is, and you can see, I think you can get a sense that the math is going to be very simple given all the results we've had before. This is going to be approximately normal, and then we already did the normal test, and this is going to be just like the normal test. And boy, is this easy. You get the MLE, you get the standard error from the Fisher information, you reject it, that's big, you're done. So you can see the appeal of this. We're not going to prove that it's got certain optimality properties and so on, but it certainly seems like a reasonable test. So on Monday, we'll do this Wald test. Then what happens though if beta is a vector? You can't use this. That's what the likelihood ratio test is for. And then we'll talk about the permutation test. Very cool. Very cool. Any questions? I hope to get you your test scores very soon because the midterm grades are due, and the graders are working hard to get them. So watch Blackboard. I guess they'll put them on Blackboard and we'll get the grades.